So let me put onto the board here the notes. So we are starting with the side that has the fill in the blank. So this is going to be a kind of stepping point for us. So we had all the past couple days, we're learning how to draw Lewis structures, but now we're going to take that and we're actually going to make shapes out of them. It's called molecular geometry. So knowing how to was kind of step number one, which is why it's important that you understood how to do it. Step two is actually applying shapes. So we're going to fill all of these in together. So first of all, let's even look at VSEPR theory itself. Okay, VSEPR stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion. So let's kind of break that down. Where is your valence shell? Outside, yeah, your outermost shell. All your valence electrons are residing in a valence shell. Electrons all carry a what charge? Negative. Good. So if you have a lot of electrons together, what are they going to do with their charges? They're going to repel each other. Yeah. So this is a way that is going to reduce. You have all of those atoms with all of those electrons, and they're all being shared. That's what covalent is sharing. So they're going to repel, and they're going to create shapes because of that. Okay. So they're going to kind of orient themselves in a way that minimizes how much it's going to want to repel all of those electrons from each other. Okay. So there's two types of pairs here. There's bonding pairs and lone pairs. Okay. Bonding pairs and lone pairs. Bonding pairs do exactly what they say they do. They bond. They're being shared. So if you have a bonding pair between two atoms, you have a pair, so two electrons that are being shared between both. A non-bonding pair is called a lone pair. A lone pair is still on that atom. It still counts towards its wanting 8 in its outer shell. It's just not being shared with anything else. And lone pairs repel more strongly than bonding pairs do. So we just mentioned all of these electrons want to repel each other because they all have negative charges. However, lone pairs tend to repel a lot more than bonding pairs do. And I'm going to show you what that looks like here in just 1 second. So a lot of times when you draw a Lewis structure and there's lone pairs involved, you're going to see how that changes the shape. Okay. So lone pairs, I just mentioned, are going to repel more strongly. So they reduce the bond angle. The bond angle is just the angle with which all of these atoms are to each other. And again, when we get to the shapes part of this, I will show you what that looks like. So lone pairs repel more strongly. They reduce the bond angle, thus shapes. Because they have a more repulsive force than bonding pairs do, you're going to start to see different shapes take place here. All right, so in order to determine what shape it is, step number 1, you draw the Lewis diagram. That's what we have been practicing. Okay, so that's why it's super important that you understand how to draw them, because that's only part 1 when it comes to shapes. The next thing that you are going to do is figure out how many bonding pairs and lone pairs are on the central atom only. I want you to circle or highlight central atom, because when shapes come into play, I only care about that central atom. All of those atoms surrounding that central, my terminal atoms, they don't count as far as bonding and lone pairs go. So we're going to kind of ignore those, and you'll see as we go through this what that looks like. And then once you have figured out how many bonding pairs you have, how many lone pairs you have on that central atom, you can take your list of shapes, and then you can kind of figure out what shape it belongs to. Okay, there's going to be 8 common shapes. Okay, 8 common shapes. So you need to be familiar with your 8 common shapes. We have a quiz over this next Friday. Okay, so we're going to not only draw Lewis structures, we're going to redraw them into what their actual shapes look like. So what I want you guys to do is flip your paper over, and we're going to fill these in together. Okay, couple things though. That very first column, total valence electrons, I'm going to skip that for now. I am going to have the Lewis structure drawn for you, and then I'm going to redraw it because sometimes when you have shapes, they're going to look a little bit different. So you're going to have 2 drawings per shape. One that we draw the way we draw it now, and then you're going to have a new shape. Okay. So the very first one is called linear. So underneath atoms bonded to the central, I want you to put 2. Underneath lone pairs, I want you to put 0. So 2 and 0, fill it in on your paper. Now I have BEH2 on my paper, or on my screen, but we're going to do BEF2. Okay. So I'm going to show you what this looks like as far as the shape itself goes. So 2 on that central, 0 lone pairs. So for this first one, whoops. All right, my computer is, what the heck? My computer is spazzing. Hang on. All right. What? Stop it. All right. This is what I want you to draw under Lewis structure, BEF2. This is what it looks like. Okay, and I want you to draw it just as it sees on the board. Okay. BEF2. So when you draw it, this is how you would normally draw it, maybe, but this is how Lewis structures are going to look like for now. We're going to start to redraw them so that they actually look like the shapes that they are. Now, some of these, when we redraw them, they're going to look the exact same. This is in one of those examples. So BF2. I don't know why my computer is having an aneurysm. BF2. All right. So as a Lewis structure, it looks like this. When I tell you, you're going to count the number of bonding and lone pairs. Guys, right here, this is a bonding pair. This is a bonding pair. So I had you guys fill in 2 bonding pairs, 0 lone pairs. Are there lone pairs on my outer atoms? Yes. Do I care about those when it comes to shape? No. I only care about lone pairs on my central, and in this case, I have none. So I'm actually going to redraw this. So underneath where it says draw shape and give bond angles. So in this case, guys, it's going to look the exact same. Okay. So if you were to redraw it so that it actually looks like linear, you're going to draw it exactly as you would have because there's no lone pairs on that central. There's nothing really acting on it differently. This is what your Lewis structure looks like. This is linear. This is 180 degrees. Okay. So linear, 180, straight line, straight across. Your Lewis structure and your shape both look the exact same. Okay. All right. Let's see if we can get back to this without it absolutely spazzing. Shape number 2 is called bent. So fill in, name of shape is bent. 2 atoms are bonded to the central, 1 lone pair. 2 atoms bonded to the central, 1 lone pair. Okay, 2 atoms on that central, 1 lone pair. And it kind of shows you, these are very 3D shapes. It's really hard to see what these actually look like when you're just drawing them flat on your paper. So I included kind of pictures of what it looks like. The ones that have a really big bubble looking thing, those are lone pairs. I said lone pairs are going to repel a lot more strongly. So in bent, as its normal shape, this is how you would draw a bent Lewis structure. Okay. So this is how up until this point we would have drawn this. So under Lewis structure, this is what you can draw. All right, so when it comes to shapes, again, I care about bonding and lone pairs. So again, here is my bonding pair. I've got two of them. So 2 atoms bonded to that central. There's my 2 bonding pairs. And then here is my lone pair. Lone pairs, I said, repel more strongly. So what happens is that these actually push down on these chlorine atoms. They push down on that bonding pair. So we're going to redraw this into the shape that actually reflects a bent shape. So here's my SN, and this Cl and this Cl get shoved to the bottom. Okay, I mentioned in the notes initially, I said lone pairs reduce the bond angle. Well, this is the reduced bond angle. Okay, and it's because this lone pair shoves down those bonding pairs. So it's similarly, you guys ever had to go on vacation and do you have siblings? You ever have to share a bed with a sibling and they like push you to like a tiny corner of the bed? That's how this is working. The lone pairs are that annoying sibling that's like shoving you to the corner of the bed, and the bonding pairs get shoved down. So lone pairs repel more strongly. So this is called bent. Okay, and you would redraw it in a way that actually looks like that lone pair is acting on those bonding pairs. So the bond angle is just less than 120 degrees. Okay, bent, less than 120. I have one lone pair pushing down those 2 bonding pairs. All right, shape number 3. I have something called trigonal planar. Trigonal planar, 3 bonded to that central, no lone pairs. 3 bonded, no lone pairs. Okay, this one has a 120 degree bond angle. Trigonal planar. So in trigonal planar, this is maybe how you drew this one, or maybe you would have had the F up here. That doesn't matter. This is our 3 surrounding my central. Okay. So here's my 3 bonding pairs. 1, 2, 3. There's my 3 bonding pairs. There's no lone pairs here. So what happens is I am going to have, you can draw this 2 different ways. It kind of depends, whatever you prefer is fine. So because everything is kind of get equal space, there's no lone pairs to contend with here. So everything just kind of spreads out as evenly as possible. So you can either draw it with 2 F's up and 1 F down, or whatever molecule you're drawing, 2 up, 1 down. Or you can also draw it so that you have 2 down and 1 up. So it does not matter. They're both the same thing. It's just showing that everything gets equal space. Everything is 120 degrees. So however you want to draw it is fine, but you would redraw this one to reflect. And again, this is trigonal planar, and it's 120 degrees. 3 bonding on that central, no lone pairs, trigonal planar. And one thing I want to mention about this one, and we just did the example with bent, sometimes with the bent and the trigonal planar, the central atom is okay with less than 8. Okay, sometimes that happens. If that were to happen, I would tell you, hey, this is an exception. Because in this case, boron is only holding 6. Okay, 2, 4, 6. And it's okay with that. Okay, sometimes it's not okay with that. But in this case, this is an example in which this molecule is. So if there's ever an exception, I will tell you that it's okay with less than 8. Okay, just so that you have that as a reference. All right. That was trigonal planar. Next one is called tetrahedral. Tetrahedral, you have 4 surrounding the central, 0 lone pairs. 4 surrounding the central, 0 lone pairs. And I want you to take note of what that 3D picture looks like on the slide, because when we draw it, it's going to look like a big old plus sign. Guys, that's not what it actually looks like in real life. Okay, it's a very 3D molecule. It's not going to be this way. It's going to look like that. Okay, so I know it's hard to visualize these as being 3D because you're just drawing them flat on your paper, but they are 3D. So look at that picture. You can kind of see how it's going to look different in real life than what you're actually drawing on your paper. Okay, so this one's called tetrahedral. So in this case, tetrahedral, you have 4 surrounding that central, 0 lone pairs. So there's no lone pairs for this one. It's hard to redraw it really to look any different. So again, I'm counting my central only. So here's my 1, 2, 3, 4 lone pairs. I'm sorry, 4 bonding pairs, no lone pairs. Okay, so when I redraw this, I'm going to draw the exact same thing. It's hard to draw that any differently than what you already see. So I told you it kind of looks flat. But again, if you looked at that 3D drawing on that slide, it's not flat at all. Okay, so your Lewis structure and your shape pretty much look the same. There is potentially something you might see, and I'll draw it for you. You don't have to do this, but sometimes maybe in a textbook or maybe on a paper that you might have, sometimes it's drawn like this, and it kind of is supposed to show you that it's not flat. So it looks like this one's like coming out of the screen at you. This one's going back into the screen or your paper. So sometimes you'll see it like that just to show that it's 3D. You don't have to do that. You can just redraw it as you see it. But if you see it that way, that's just what it's trying to show you. Okay. So again, this one's tetrahedral. And it was 109 degrees for the bond angle. All right. You guys still with me? Doing great. All right. Next one. This is called trigonal pyramidal. Trigonal pyramidal. 3 atoms on that central, 1 lone pair. 3 atoms on that central, 1 lone pair. So again, in the picture, you can see that really big looking bubble on top. That's the lone pair, and it's just to try and show you that it actually is spreading out and it takes up a lot of space. Okay, bond angle for that one is 107 degrees. So as a Lewis structure, looks like this. Okay, maybe you have that lone pair on the bottom and that hydrogen on top. So here's my 1, 2, 3 bonding pairs. Here's my 1 lone pair. Okay, so 3 on that central, 1 lone pair. So technically, this nitrogen, remember kind of said, think about it as 4 sides. It has something occupying all 4 sides. 3 of them are bonding and then 1 of them is not bonding. Okay, so you're going to redraw this because of that lone pair. What's that lone pair going to do to those hydrogen? Yep, it's going to shove them down. So now when you redraw this, all of those hydrogen are getting shoved down. Okay, when you redraw that shape, so this is what you're going to start doing now that you know shapes. You're going to be redrawing them in a way that reflects those shapes. All right, and I want to show you something really quickly, and I want you to understand what's happening. If I go back to tetrahedral, guys, look at tetrahedral. This carbon has something in all four sides, right? They're all bonding. You see that? You agree with that? My bond angle is 109. Yes? Yes. 4 spots around this carbon, all 4 bonding. Nitrogen has all 4 spots also taken, but only 3 of them are bonding, and you have 1 lone pair. My lone pair repels more strongly. Lone pairs reduce the bond angle. Tetrahedral was 109 because it had all 4 bonding. Here's this lone pair. What did my bond angle do? It went down because lone pairs repel more strongly and the bond angle goes down. So that's what I meant by it reduces the bond angle. Okay. If you think of every central as a 4-sided thing, there potentially could be something attached to all 4 sides, whether it's a bonding pair or just a lone pair. Okay. So I want you to kind of pay attention to that. These angles are changing because the number of bond and lone pairs are changing. Okay. All right. I am going to go next to H2O. Okay. This one, also called bent. I don't know if they ran out of names and just decided to reuse one, but this one is also called bent. Okay. This one, though, is different than the first bent. The first bent had 2 on that central and 1 lone pair. This one has 2 on the central and 2 lone pairs. Okay, so this one's 2 and 2, and the first bent that we came across was 2 bonded to that central with only 1 lone pair. So because it has 2 lone pairs, it's going to shove those bonding pairs down even more. So H2O is the example. Notice the bond angle is 104.5. Okay, so this is a second bent, but it is different. The name is the same, but it is different in this case. So here is H2O as a Lewis structure. Okay. H2O as a Lewis structure looks really flat. Here's a bonding pair. Here's a bonding pair. Here's my lone pair. Here's my lone pair. When you redraw this to make it look like this bent, the H's get shoved down towards the bottom. And now because there's 2 lone pairs, they're both going to want equal space. So you kind of do these like this. It kind of gives them equal space while they're shoving down those bonding pairs. Okay. This one was also bent, but notice the bond angle is less. Our first bent was less than 120 was the bond angle because it only had 1 lone pair. This one has 2 lone pairs, so our bond angle is much smaller at 104.5 because it's shoving them down further. Okay, so this is the second bent. This is the only repeat name. I don't know why they repeated bent, but they did, and here we are. All right, we have 2 more to go. I'm actually going to skip PCl5 for a second. And I'm going to go down to octahedral. So go down to SF6 for me. And I'll come back to PCl5. All right, SF6 has 6 surrounding the central, no lone pairs. 6 surrounding the central, no lone pairs. Bond angle is 90 degrees. For anything octahedral, if it has 6 things attached to it, and each of those bonding is 2, how many total electrons are on that central atom? 12. Sometimes, and I mentioned this when we first started going over this, sometimes your central atom can expand and hold more than 8. This is a case in which it would do that. Again, I would tell you that. This is going to hold more than 8, and that's okay. Okay? So this is called octahedral, 6 surrounding the central, no lone pairs. So again, you're not really going to be able to redraw this probably much different than you would as a Lewis structure. Okay? But here are my 6 bonding pairs. 1, 2, 3, 4, 5, 6. Okay, there's my 6 bonding pairs. And again, you're probably going to redraw it as best you can. It's just supposed to show that everything has equal space. There's no lone pairs to contend with here. So everything gets 90 degrees. So these are all 90 degrees away from each other. So again, how you draw this probably won't differ much from what you would have drawn it as a Lewis structure. And I know that it's a pain to put all of these on the outer, all these electrons, but you have to do that. You can't do a Lewis structure without finishing it off like that. Okay? So octahedral, again, this bond angle is 90 degrees. Yes, the central atom will hold more than 8. Yes, that is okay.
So whenever it says octa, why is it like that?
Why is it 6 and not 8?
Yeah.
Great question.
That's what it's called.
That's what it's, yeah. That's why we have 2 bends. That's why octa has nothing to do with 8. That's a great question. All right, last shape. You guys have done so good. Last shape is PCl5. Now, I actually don't even have a slide for this one, so I'm just going to do it on here. PCl5. All right, in this case, you have 5 bonding. So 5 bonding to that central atom here. 0 lone pairs. 5 bonding, 0 lone pairs. This is called trigonal bipyramidal. Trigonal bipyramidal. And it actually has 2 bond angles. It has 90 degrees and 120 degrees. Again, there's my 5 bonding. I have no lone pairs. You're going to draw it the same exact way as you do your Lewis structure, simply because there's not really a way to redraw that. If you want to think about this, though, like if you held your hand out flat, like that would be, you would have like 4 in the middle, and then you kind of have 1, actually 3 in the middle, and then like 1 coming up top and 1 coming off the bottom. So again, this is hard to picture. This is not flat, but this is the last shape. Trigonal bipyramidal, 5 surrounding that central, 0 lone pairs. Everything gets equal space-ish, 90 and 120. It's the way that it's oriented. Okay, so I want to show you really quickly just again some of these 3D shapes. This would be trigonal pyramidal. There would be a lone pair up here, and these 3 get shoved down just because it's not flat. It's very 2D. Now, one thing I want to mention before I'm done. I mentioned at the beginning, you count double and triple bonds as a single pair. So what I mean by that, CO2, even though there are 2 bonds here, 4 total electrons being shared on both sides, I still only count this as 1 atom bonded over here, 1 atom bonded over here. So I still only have 2 atoms on that central. So this is an example where even though there's a double bond, I'm still going to say that it's linear because there's 2 bonded to that central, 0 lone pair. So that's what I meant by count double and triple bonds as a single thing. Oh, all right. You guys did awesome. Makes sense for you? Good. All right. Nice job.